Usually, when you bite into this crisp, pristine apple from the grocery store, you picture like a wholesome, sunlit farm, you
Yeah,
know?
absolutely. The classic idyllic farm.
Right. You imagine gentle rain, a farmer on a tractor, maybe some birds chirping. It's this very comforting illusion. I mean, we really like our food origins to feel, well, uncomplicated.
Yeah, we want to believe nature just sort of effortlessly hands us this polished, ready-to-eat fruit on a silver platter. But if you step into an actual orchard in early spring, like before a single leaf is even open,
Mhm.
that peaceful picture completely shatters
It really does.
because you are standing in the middle of a high-stakes, microscopic war zone.
A full-on microbial battlefield, hidden right in plain sight. And that is exactly what we are unpacking in today's deep dive. We've got this fascinating stack of sources, specifically field notes and observations from a class trip for a course called Nature and Innovation.
Yeah, those notes are wild.
They really are. And our mission today is to explore this surprisingly crucial yet incredibly labor-intensive step in orchard maintenance, a step that has to happen right now before the spring bloom.
And to anchor all of this, we're following these two university students, Kesser and Steen. They're out there just freezing their hands off in an apple orchard this morning.
Ugh, sounds miserable.
Right. But their main job isn't planting new saplings or, fixing irrigation lines. They are scouting. They've been deployed on a literal hunt for something the agricultural world calls fruit mummies from last season.
Which, I mean, that sounds like a B-movie horror plot.
It really does.
But the stakes are incredibly real. This seemingly basic hunt for dried up, leftover fruit, it involves like competitive microbial warfare, secret smartphone Google searches during a lecture, and this huge plot twist realization that the beautiful apple blossoms in this orchard aren't actually meant for us humans at all.
Yeah, it completely flips the traditional agricultural model on its head.
Ah.
But to understand why Kesser and Steen are out there squinting at bare branches trying to spot these tiny brown husks, we kind of need to look at the underlying philosophy of the orchard they're standing in.
Right, because this particular plot of land operates, well, in direct defiance of standard commercial farming economics.
Exactly. Normally, managing an orchard is basically an exercise in reverse engineering a financial outcome. You're looking at the cost of manual labor versus the desired yield.
Like, can you afford to pay a crew of workers who might make mistakes and cut the wrong fruiting branches?
Spot on.
Yeah.
And often, commercial operations decide they just can't afford that risk. So they rely heavily on chemical intervention to manage the crop load.
Chemical thinning agents, right.
Right. They use these synthetic sprays during the bloom. And these sprays intentionally disrupt the tree's photosynthesis, or they alter its hormones to force it to drop a huge percentage of its flowers.
Just drop them right on the ground.
Exactly. Because the logic is simple. Fewer apples mean the tree funnels all its energy into growing the remaining fruit into those giant, uniform, blemish-free orbs you see stacked in premium supermarket displays.
But the orchard Kesser and Steen are standing in is owned by a woman referred to in our sources simply as Oma. And Oma, she does not care about premium supermarket aesthetics.
Not even a little bit.
She grows heritage apple varieties, the kinds with the long seasons, specifically meant for baking dense tarts, pressing into fresh juice, or fermenting into cider and vinegar. And Oma's core philosophy is just a radical departure from the norm.
It really is.
He believes the apple trees are actually meant for the insects and the bees. Human consumption is just like a happy byproduct.
Right. She treats her orchard less like a sterile biological factory and more like a bustling metropolis. The trees are the essential infrastructure, and the diverse insect populations are the citizens keeping the local economy running.
Wow.
Yeah, in a conventional setup, insects are pests that reduce the profit margin. Here, they're the primary stakeholders.
Okay, let's unpack this. It's like treating the orchard as a bed and breakfast for bugs rather than an agricultural factory.
That is a perfect analogy.
And because she treats it like an ecological metropolis, she refuses to use that standard synthetic chemical shield. Like,
Yeah.
she doesn't soak her trees in chemical thinners or harsh fungicides. Instead, she leans into biological support.
Heavy biological support. She uses thick applications of seaweed compost to enrich the soil microbiome, and she utilizes these Korean natural farming techniques.
Which is an incredibly resilient way to farm, but I imagine it leaves the trees highly vulnerable in the early spring, right?
Absolutely. By removing the chemical safety net, OMA has to replace it with smart, preventative physical labor. That vulnerability is the exact reason Kesser and Steen have to be the physical shield today.
And the sources explicitly point out the practical humor of this situation. I mean, this is a backyard orchard, not a clean room at a microprocessor plant.
Right, they aren't wearing hazmat suits.
Exactly. You have these young students out there, and they shouldn't be messing around mixing dangerous chemical fungicides. And no, they definitely aren't dragging a vacuum cleaner with a HEPA filter across the morning due to clean the grass under the trees either.
That would be a sight.
They are just using their eyes and their freezing fingers to perform the mummy hunt.
And the directive is simple but tedious: walk the orchard and physically detach any shriveled, dried up apples left over from last year's harvest that are still clinging to the branches. And, the clock is ticking.
They are racing against a weather trigger, aren't they?
Yes, a very specific meteorological trigger. They have to finish before the spring rains arrive and the ambient temperatures begin to rise.
So we know fungal spores are pretty much everywhere in any outdoor environment, but the mechanism of this specific weather trigger is super fascinating. It's not just getting wet.
No, it's a precise combination. Moisture plus a temperature threshold acting like a microscopic spring-loaded trap.
How does that actually work mechanically?
The biological mechanics are brilliant. The moisture from the spring rain rehydrates the dormant fungal tissue inside those dried apples. As the temperature hits the optimal range, the fungus builds immense internal turgor pressure within its fruiting bodies.
Like blowing up a balloon too much.
Exactly. Eventually, that pressure forces the fruiting bodies to rupture, literally ejecting millions of microscopic spores into the air currents. Once airborne, they ride the wind invisibly, landing on fresh, vulnerable green tissue like a newly opened leaf or a delicate blossom to start the next cycle of infection.
Okay, here's where it gets really interesting to me, and I have to push back a bit on the mechanics of this cleanup.
Sure, go for it.
If the primary concern is leftover apples harboring dormant fungus, what about the hundreds of apples that naturally dropped into the tall grass last autumn? Like, if they aren't out there with a HEPA vacuum, how is the ground not a massive contamination zone? Why are these specific mummies hanging on the branches the actual ticking time bombs?
That's a great question. The distinction lies in the microenvironments. The ground is a highly active, aggressive zone of decomposition.
Oh, because of all the bugs.
Right. You have an army of detritivores, earthworms, pill bugs, soil bacteria, and competing soil fungi. When an apple falls into the grass, it is rapidly digested. The carbon is cycled, and the pathogenic fungi within the fruit are outcompeted and broken down by the sheer biological weight of the soil microbiome.
So the earth basically just consumes the threat.
Exactly. But the apples up in the tree canopy completely bypass that digestion process.
Because they're just suspended in the air.
Right. The autumn winds wick away their moisture, halting the decomposition process entirely and initiating rapid desiccation. The apple shrinks into a hard, shriveled husk. And because it dries out rather than rots, the fungus inside doesn't die.
It just goes to sleep.
It enters a state of deep dormancy, becomes this perfectly preserved time capsule of infection, sitting on a branch at point-blank range to where the new, vulnerable buds are going to emerge.
Which means they are literally harboring the enemy inside the gates. They have to be removed from the garden entirely. I bet you can't even toss them into the compost pile, right?
No way.
Yeah.
Because they might not break down fast enough before releasing spores. They have to be gone.
Man, to truly grasp the destructive capability of these tiny, dried husks, we need to look over the shoulder of our student Steen.
Ah, yes. Steen's secret research.
Right, so paint this picture for me. Professor Hendricks is standing in the middle of the orchard delivering the official lecture, and Steen is doing what curious students do.
He's hiding his mobile phone behind his jacket to block the glare, secretly Googling the exact pathology of these mummies.
He wants the hard biological data, and he finds the specific culprit they are hunting, this pathogen known as yellow Monilia, or Monilia fructigena.
It sounds so lyrical, Monilia fructigena.
It really does, like a magic spell.
But the physical manifestation is brutal. Yellow Monilia causes the fruit to rot while it's still attached to the tree. Steen reads that it presents as small, raised pads of yellow spores that grow outward in these perfectly uniform, concentric rings across the skin of the apple.
Ew. And the timing of the infection is just insidious, and it frequently flares up right before the autumn harvest.
Yes.
Like if you've ever found a bizarrely shriveled, dusty, lightweight lemon or apple hiding in the very back of your refrigerator's crisper drawer.
Oh yeah, we've all been there.
You've witnessed a similar fungal survival mechanism. If a farmer unwittingly picks an apple with a
It has the capacity to quietly wipe out a massive portion of your stored food supply, long after you thought you'd secured a successful harvest.
But wait, how does the yellow Monilia actually penetrate the apple in the first place? I mean, an apple skin is this evolutionary marvel designed specifically to protect the fleshy, seed-bearing interior from
Right,
pathogens.
it's basically armor.
The fungus can't just magically phase its way through the waxy cuticle, can it?
No, it requires a mechanical breach. The fungus is highly opportunistic, but it lacks the physical tools to drill through intact skin.
So it needs help.
Exactly. Now, that breach can occasionally come from environmental trauma, like a heavy hailstorm, intense rain causing the fruit to swell and split, or even chemical spray burns in a conventional orchard. But in a biodiverse setting like Oma's, the primary entry wound is almost always created by an insect sting.
So the insects are acting as unwitting accomplices to the fungus.
Yes. Specifically, the larval stage of certain moth species. The apple codling moth, the plum fruit moth, and the hawthorn sun moth are the primary vectors.
Okay, so how do they get in?
The adult female moth lays her eggs on the surface of the fruit. When the larvae hatch, their very first meal is the skin of the apple. They physically chew their way into the fruit, completely breaking that protective seal.
Oh, wow. So what does this all mean? The safecracker analogy fits perfectly here. The apple is the bank vault, and the waxy skin is the steel door.
I love that analogy.
The moth larvae act as the safecrackers drilling right through the door, and once the vault is cracked open and compromised, the yellow Monilia fungus swoops in right behind them to actually steal the contents, rotting the fruit from the inside out.
That is exactly it. The insect provides the initial breach, the fungus executes the hostile takeover, and in many agricultural settings, even those using organic biological controls, you fight the safecrackers first. You deploy a countermeasure called BT, or Bacillus thuringiensis.
We hear about BT a lot in natural farming, but the mechanism is wild. It's a naturally occurring soil bacterium, right?
It is. And the brilliance of BT lies in its biochemistry. The bacterium produces these microscopic crystalline proteins. When a moth caterpillar ingests these crystals, the highly alkaline environment of the caterpillar's digestive tract dissolves them, releasing a targeted toxin.
Ouch.
Yeah, this toxin essentially punches microscopic holes in the gut lining of the larvae, stopping them from feeding almost immediately.
So you neutralize the safecrackers, you save the vault.
In theory, yes.
But even if you manage the moth population perfectly, you still have to deal with the fungus directly. Because if yellow Monilia establishes a strong enough foothold in those mummies Kesser and Steen are hunting, the fungus can do something terrifying.
Oh, it gets worse.
It doesn't just stay in the dried apple. The mycelial network can actually grow backward, traveling through the stem of the mummy directly into the living wood of the tree's branch.
Once the fungus enters the vascular system of the branch, the tree itself is compromised, leading to cankers and dieback. That is the critical reason why the physical removal of the mummies is the ultimate non-negotiable countermeasure. You have to physically sever the bridge between the dormant pathogen and the living tree.
Okay, this introduces a massive tension into Oma's philosophy, though. We know the yellow Monilia fungus is aggressive. We know it only takes one microscopic scratch from a surviving moth larva and a little bit of warm spring rain to initiate a devastating chain reaction.
Right.
So what happens when Kesser and Steen inevitably miss one? I mean, they're human, their hands are freezing, and the mummies blend in perfectly with the brown branches.
It's bound to happen.
Exactly. When the spring rains arrive and Oma refuses to use synthetic fungicides, how does she stop the airborne spores?
This is where Oma's management style elevates from simply letting nature take its course to highly strategic biological warfare.
Yeah.
She anticipates the human error. If the environmental conditions heavily favor the fungus, she intervenes with an ingenious backup plan.
And the notes detail this Oma actually rigs up a sprinkler system directly in the canopy of the apple trees.
She does.
But she isn't pumping municipal water or deep groundwater. She pumps collected rainwater, heavily infused with those Korean fermented herbs Kesser and Steen were experimenting with. And she times the deployment with absolute precision. She runs the system right before and exactly during the blooming phase.
The timing is critical because the open blossom is arguably the most vulnerable point of entry for pathogens.
Why is that?
Well, the nectaries of a flower are rich in sugars, and they completely lack the protective waxy cuticle of a leaf or a fruit. By spraying this fermented rainwater, she is employing a principle called competitive exclusion.
Walk me through the biochemistry of that, because usually the rule is to leave the flowers completely alone so the bees can pollinate without interference.
True, but the fermented herb mixture isn't just a nutrient tea. It is a dense, hyperactive culture of beneficial microorganisms, heavily dominated by lactic acid bacteria. She is intentionally flooding the tree canopy with her own microscopic army.
An army of good bacteria.
Yes. When this liquid lands on the sugar-rich stigma of the apple blossom, these beneficial microbes reproduce exponentially. They rapidly consume all the available biological real estate and all the microscopic exudates the flower produces.
They are occupying the territory before the enemy even arrives.
Exactly. So when the yellow Monilia spores inevitably launch from a mist mummy and land on that same blossom, they find zero bioavailable calories.
There's nothing to eat.
Nothing. There is no room to establish a foothold, and no food to fuel the growth of their germ tubes. The fungal spores simply starve to death on the surface of the petal, completely outcompeted by the beneficial bacteria.
It is literal biological warfare, a siege tactic playing out invisibly on the surface of a delicate flower petal. That is mind-blowing.
It's incredible.
And this hyper-vigilant philosophy of preventing the fungus at all costs dictates the rhythm of the entire year, right down to how the harvest happens in the autumn.
It does. The safecracker principle still applies months later. The fungus always needs a wound. So when it finally comes time to pick those apples, the workers are required to harvest them as gently as humanly possible.
Which means no tossing them into buckets.
Nope. A single micro scratch from a careless fingernail or dropping an apple an inch too hard into a wooden harvesting basket creates a microscopic bruise beneath the skin.
And that invisible bruise is a structural compromise. It becomes the entry point for late-stage Monilia to sneak in, ride the apple into the winter storage cellar, and initiate the dry rot phase we talked about earlier.
Precisely. And the threat of the fungus also dictates the storage parameters. The apples must be kept at the absolute lowest temperature possible without actually freezing the cellular structure of the fruit.
Because cold kills the fungus.
Well, cold temperatures do not kill yellow Monilia,
Right.
but they dramatically depress its metabolic rate. Every single step of the agricultural year, from students pulling mummies off branches with freezing fingers in the spring, to flooding the canopy with competitive lactic acid bacteria, to handling the mature fruit like fragile glass in the fall, is architected around managing this one invisible, opportunistic fungal threat.
Bringing this massive biological cycle back to your own life.
Yeah.
Even if your only interaction with an apple is, tossing it into a plastic produce bag at the grocery store, understanding this delicate, invisible ballet completely changes how you view your food.
It really gives you a new perspective.
It does. Knowing that a single tiny scratch or one overlooked, dried up apple from a previous season holds the power to completely devastate a future harvest.
Yeah.
It gives you a profound, almost humbling appreciation for the food that actually survives the journey to your table.
You are looking at the resilient survivor of a massive multi-front microbial war that has been raging since before the leaves even opened.
Yeah.
The fact that an apple exists at all, without being consumed by a moth larva or hollowed out by a fungus, is a testament to either heavy-handed chemical intervention or, in Oma's case, an incredibly attentive, labor-intensive partnership with the ecosystem.
Absolutely. So to quickly recap our journey through the orchard today, we started alongside Kesser and Steen on a freezing spring morning, understanding why hunting for those insidious fruit mummies is essential to physically severing the cycle of infection.
Right.
We broke down the mechanics of the safe-cracking moths that breach the vault for the yellow Monilia fungus. And we ended with Oma's brilliant canopy sprinkler system, utilizing competitive exclusion to fight bad microbes with good ones, all to protect a harvest that she ultimately believes belongs to the bees anyway.
It's a beautifully complex, interconnected system. And if we elevate this biological cycle to a broader perspective, it leaves me contemplating the mummies in our own lives.
Oh, I like where this is going.
Well, we've seen how a single, unnoticed, dried-up remnant from last season can quietly preserve enough dormant, destructive potential to dictate the health of an entire future ecosystem.
Yeah.
This raises a really compelling question. What other mummies, perhaps outdated ideas, old habits we haven't quite discarded, or unresolved issues we've left hanging in our own personal canopies, are we leaving dormant, just waiting for the right meteorological conditions to spread and infect our future growth?
Wow, that is a phenomenal question to leave hanging, and exactly why we love unpacking these sources. Thank you so much for joining us on this deep dive. Go check your own branches, clean out those old mummies, and we will catch you on the next one.